Welcome back to day 2. I had a good time giving the talk yesterday and also meeting with a group of the students afterwards. Excited to hear about all the different things that are going on here. Today, I'm going to walk through sort of introduce you to the concepts of discretization for those who aren't familiar with it, and in particular go into radiation transport and how we discretize that. And then look at the traditional way of doing neutronic simulations, which is a multi-step approach, and show how there's a similar multi-step type of approach in fuel performance and thermal fluids, and then start talking about how we solve those in a coupled physics standpoint. So, as with yesterday, I went in detail on a PWR and then briefly touched on other reactor types. I'm going to sort of try to go in detail on radiation transport, and then we'll briefly touch on how there are connections and similarities in the other physics fields. So we talked about operator notation and radiation transport. We have our 1 over the speed. d psi dt is the rate of change of number of neutrons. We have the leakage streaming out of the system and collision operations, where both of those are going to remove neutrons from that given set of a particular direction of travel and neutron energy at a particular location at a moment in time. And then we have 2 different sources for how they can appear at that given energy, direction, location, and time. And with those, we can define a fixed source problem, time-dependent fixed source. If we just had no time dependence but fixed source, it would just be L psi equals Q. We have a full time dependent with the scattering and fission sources, or if we're steady state, we've defined an eigenvalue problem where there is no source at all. And so in this, these are all analytic functions. And so this is something that if we said, let's collapse this to a one-dimensional problem and let's pick one direction and let's pick one energy, then we could, and we knew what our material properties were, our sigmas, then we could define an analytic solution for that. So we haven't done any spatial discretization at all. The concept of discretization is we approximate the analytic solution. In the analytic solution, you analytically derive what the solution is everywhere. But those analytic solutions, as you get to 3D with energy and space and time dependent, get very, very intractable very quickly. And so we're going to try to break this up into solvable chunks. And with radiation transport, you have to break up the spatial domain, the direction that neutrons are traveling, and the energy the neutrons have at the moment in time. Each one of those has to be approximated. So if we said we had some geometry, and so let's say this is a BWR assembly with the control blades inserted. So you see this is the control blade. Each one of these has little B4C absorbers inside of it. And we have lots of different fuel pins and water channels, and the low density water in the center and the higher density water out on the outside. And we say this is our material definition for looking at this one assembly. Well, we would need to break it up into spatial regions if we're going to discretize this. And so we put some type of mesh, some type of grid over this. In this case, we took every cylinder and we made the cylinder a 16-sided polygon, and we overlaid sort of an XY grid. And we said, now we can treat each one of these individual grid cells on its own and say, okay, now how would I solve for the problem in that individual mesh cell? So each mesh is going to have some uniform material definition to it. And then we have to approximate what the problem. And so there are a variety of ways of doing this. As a quick intro, if we had a continuous finite element and we had a one-dimensional problem, what we do is we break this up into a bunch of individual elements. So these are spatial cells. And there's a node that is the boundary between each of those spatial cells. And we'd say, I want to solve for what the solution is at each one of the nodes, and I'm going to approximate and assume that it's a linear shape between each of those nodes. So if the analytic function was some smooth quadratic, the approximated linear finite element would have these piecewise linear pieces throughout it. On the other hand, we could do a finite volume type of approximation, where what we're going to do is we're going to look at the volume over each mesh cell, and we're going to integrate that volume, and then we have to say, okay, now how am I going to approximate what is happening at the surfaces? And so this would kind of look like this, where if we had some square mesh cell, we'd say we had some material in here, and we want to integrate the solution in here, so we get the average on the inside right, and we just need to approximate how many neutrons are flowing in this side and flowing out that side and the other faces. And so the finite volume, you define a cell and compute what is happening at the interface. With finite element, you say, I want to compute the solution at locations and then assume a shape between those two locations. Either is fine, it doesn't really matter. But with transport, one of the things that's kind of easy to see is, let's go back to our analytic type of approximation. And so if we just had the steady state fixed source L psi equal Q operator, and we said, let's define a problem so there's no scattering, no fission, no time dependence, and everything is all in one dimension. So all of the particles, it's uniform in, it's infinitely large and uniform perpendicular to that direction. Then in that one direction, we'll call it the z direction, we have a direction of travel omega z, and d psi dz, so that's this operator comes down to just omega z d psi dz, plus sigma t psi equals q. And that is an analytic function. We can analytically compute what psi as a function of z is. And so psi of z is psi at 0, e to the negative tau, plus q over sigma t, 1 minus e to the negative tau, where tau is the sigma t z divided by omega. And so then if we knew psi as a function of z, we could figure out what the average from 0 to z was. And so the average of 0 to z would just look just like that. And so now we have, if we know that this is our solution, this is our problem, we can analytically derive that one solution. But in it, we had to assume that that q and the sigma were constant. And so if we had a 1D problem with a bunch of different materials, then we could say each one of these colors is infinite in that direction and this direction. And we have a one-dimension type of problem. And let's say we have some source over here, and we wanted to see how much radiation got to the person on the other side. We'd look at each material and we'd say, okay, let's approximate each material as having one cross-section. So there's no variation in each material. And now we have a set of linked one-dimensional problems that there's an analytic solution for each of them. And so in cell 1, we had the outside of blue, we had our initial angular flux, the source that was over there on the left, and it's going to exponentially decrease as it gets to the middle. And if there's a volumetric source Q in that cell, it'll volumetrically increase until it gets to that interface between blue and orange, which we're calling location 1. And so at location 1, now that's the source for the orange cell. And so you can follow the same path. And so each one of these, you have your psi 0, psi 1, psi 2, psi 3, psi 4, psi 5, psi 6. And when you get to psi 6, you know the angular flux that's getting to that person, so you can figure out what their radiation dose is. And each of them are just a series where you're marching through in that direction. And obviously the same would hold true if you were looking at radiation that went in the other direction. So if there was scattering in these cells, then some neutrons could come into the blue and bounce and scatter and go the other way. And so you could march in the other direction, the negative omega z direction, to get the rest of it. And so if we call tau our omega z, then it would just be from 1, 2, 3, we're going that way, and then we come 3, 4, 3, 2, 1 back the other direction to cover all directions of travel. So in this way, we transform what is our continuous in space problem, L psi equals Q, to a discretized set of problems. Each chunk, we have an analytic solution to it, and we can completely invert that problem. And so inverting L is solving for psi. So psi is the inverse of LQ. And so by doing that, we've created a way where we can just create that psi is L inverse Q. But to do that, we had to approximate the cross sections of the sources. We had to say my sigma t is constant in material in cell 1. My Q is constant in cell 1. And so I had to make what might be some approximations. Maybe those aren't approximations, but they might be approximations. So we do a similar thing in the direction that neutrons are traveling. Actually, let me take a break. Questions? What questions do y'all have? Nobody? All right. Okay, so when we look at the direction that neutrons are traveling, there are an infinite number of directions a neutron can be traveling. Even in a problem where the materials are one dimension, here, even in this problem, your neutrons could travel directly at that person, but they also could come from up here down to that person, or over here from this side of the blue slab to that person. And so there are an infinite number of directions that the neutrons could travel to get to that person. And so we have to figure out some way to approximate or to discretize the direction that neutrons are traveling. Since it is infinite, we are going to choose, and so the one I'm going to talk about today is called a discrete ordinates or SN approximation. And so we're going to say psi as a function of all the directions that can be traveled at any given location R, at any given energy and moment in time, is a sum of a whole bunch of individual directions. And so if we say we're going to approximate this as a sum of maybe 10 directions, or 100, or 10,000, or 10 million directions, we're going to choose individual directions, and we're going to assume that if we have enough directions, then we will assume we've covered the full space of directions. In some ways, it is similar to the finite element approach, where you say, I'm going to solve at an individual node. Here, we're going to say, I'm going to solve at an individual direction. And then for each direction, you have to give it how much does it contribute to the overall total. And so if you break your directions up evenly, like over here on the right, if you picture this as 1/8 of the sphere, you could say, I'm going to solve in every direction where there is a purple dot. And so all of those are going in the positive X, positive Y, positive Z coordinate system. And so if you had a three-dimensional problem, you'd have the same here, here, and here, and then you'd have the same 4 in the bottom. So you'd have 8 times this number of directions to solve. If we wanted to, we could have them completely uniform, just like this. Everyone is sort of representing this box around it. And so this cell is kind of representing this area around that discrete direction, that cone of directions. But if you wanted to, you could break it up. So you could say, maybe I want a different set of directions. And so if I think there might be a lot changing in the corners, maybe I put little ones in the corner, but everything is changing very little in the middle. So I have a big giant one in the middle. There's a variety of ways that you can discretize this. But in general, all of these would have the same 288 directions in all three-dimensional space. And it's just a matter of what is that weight term that you put in front of it. Because when you want to integrate what the scalar flux is, you have to give each individual direction psi m a weight. And so we know if everything is uniform. So if psi just equal 1 everywhere, then this should equal 4 pi. Integral of 4 pi, 0 to 4 pi is 4 pi. And so these weights should all sum to 4 pi. And so if we have 2, 100, 1,000 directions, we're using both of these approximations to break the problem up into a set of individual discrete directions that we're going to solve. And so with that, for every spatial location, we would have a set of m directions in the problem. If we have I spatial cells, then what we wind up with is a set of I times m unknowns. We have a direction m at cell I that we can solve for, and each one of these has its own individual equation. And so if we were to create our scattering in here, we could have our loss, our angular flux, our leakage flux collision, our angular flux, our external source, and our scattering times phi. And so we can break this problem up now into a number of directions, number of cells, set of coupled equations. If you have a code like MATLAB, then you can formulate this in the form of a matrix. You can say, let me create a matrix, and at every cell, I have a incident piece and a total and a source, and let me put this into MATLAB, and I can say, MATLAB, just solve this for me. Do inverse of L and give me what my new solution is. That may not be the most efficient way because MATLAB doesn't like really huge problems. And so if you've ever tried to use MATLAB to solve a problem with 100,000 unknowns, it takes forever. You go to 1,000,000 unknowns and it says, no, I have run out of memory, I'm done, I'm stuck. So if we're in the range of 1,000 spatial cells and in the range of 100 directions, then you can get away with that. And you can just hand that to a math solver and say, invert this matrix, solve it for me, and take care of it. But the reality is the space and direction are a relatively easy part. Conceptually, we break our problem up into some regions. We say the material properties are constant in each region. We break our direction up into a number of individual directions. We give each direction a weighting function, and we have that set of problems that we can solve. There's entire research fields on how do you choose the directions. There's entire research fields on how do you do that All right, I have connected to my cell phone to get the Wi-Fi up and working. So we don't have the room system on for the people on Zoom. Let's see. People in the room can't see anything either, but at least I can say hello to you guys and let you know we're working on it and we're trying to get it fixed. Do you guys have on Zoom? Do you guys have any questions?
No, teacher.
We had one question here in person that I answered while everything went dark. Question was, how do you know what mesh cell size you should use? How do you decide that? For the spatial mesh, in general with transport, if you know your total cross section, your mean free path, your average 1 over the sigma total. And for most spatial discretizations, if you have a mesh cell that is less than 1 mean free path, then you are going to get a pretty accurate answer. And so if you know in each material, you need to have mesh cells that are smaller than 1 mean free path. If your problem is 1 meter big and your cross sections are have a 1 centimeter mean free path, then you know you need at least 100 mesh cells. And if it's in 3 dimensions, then you need 100 in X and 100 in Y and 100 in Z. And now you have you have a million unknowns in just space to solve that problem with a expected accuracy. And then how do you choose the number of directions and which directions? A lot of that is experience, and you develop that experience by running many calculations. And so if I have a problem, I will usually say, let me run it with 1 set of directions, and then let me add more directions and add more directions and add more directions and see if my solution is changing. And so as you get to a point, you'll see your solution is changing very little. And so you've decided I have enough directions, that's enough to use. And in some problems that might be 4 directions, and in some problems it might be 288. Let's see.
Good morning, doctor. I have one question.
Yes.
So, geometric shape is key in the design and efficiency of reactors?
The what shape?
Any geometric shape?
Oh, yes. So in general, when you're doing your spatial mesh, you should be resolving all of the geometric features and shapes. And so if you have really thin cladding, that cladding might be a millimeter thick, and you'd need to have a mesh cell to refine that millimeter thick cladding. If you have in many cases, I don't know if you guys are familiar with integral fuel burnable absorbers, but in some PWRs, they will often take a fuel pellet and spray boron on the outside, and that boron might only be 10 microns thick layer of boron. And so in that case, you need mesh cells that are on the size of 10 microns, except for the fact that boron is a really big absorber. And so because boron's mean free path is very short, you might actually need less than 10 micron mesh cells. And so you can see rather quickly, if you are trying to model an entire reactor with radiation transport, and you are resolving every one of the pieces of cladding in the reactor, and there are 50,000 fuel pins, and the reactors are meters in size. To model that entire problem, you are easily getting up to 10 to the 15th, 10 to the 18th unknowns.
And that you cannot give to MATLAB and say, please give me the answer. For that size of a problem, you would need a supercomputer just to hold the amount of memory required to hold the solution for all of those calculations.
So the future of the reactors is exciting, right?
To me, it is. I hope so. So I think we're reaching a time where we are either going to start building advanced reactors like China is doing now, or we are going to say nuclear is not the answer and renewable energy is, and let's shut down all of our nuclear reactors. They're not the solution. I fundamentally disagree with that hypothesis. I am confident we need reliable, predictable energy that is not dependent upon nature. And I also think that we have a significant need for high temperature heat sources. Right now, all of the industries worldwide use high temperature heat from burning fossil fuels to make their processes work. If you need something at 600 degrees, 1,000 degrees, you can't do that with the sun. It's not going to work. And converting all that to electricity and then trying to use electricity to get things that hot is not going to be effective and efficient at all. So I am 100% confident that the world needs nuclear energy, and we should be moving away from the old generation of light water reactors towards new advanced reactors. But the existing reactors are working great, so let's keep them working as long as we can. But I do think that, you know, the people that are in school today are going to get to see and watch and make that transition from light water reactors to advanced reactors happen.
What about the
SMRs? So yeah, so the question is, what about SMRs? Well, so there are SMRs that are advanced reactors and there are SMRs that are light water reactors. I do think there is a absolute place for light water reactor SMRs. I think that if we are going to build an SMR, it is the one that we could today just go and say, let's just manufacture this. Let's do it and let's make it. And they can operate safely. There are plenty of places in the world that need that type of energy source. And so it's a great answer, especially for near-term global warming impact. We can build big light water reactors. We can build small modular light water reactors. Both of those we can just pick up today and start building them. There isn't much research needed. But I think that long-term, there are better options, but long-term might start in 20 years and it might start in 5 years. That we're not sure about yet. Let's see, I wonder is there any way, could I plug my computer into this TV to display on this TV?
¿Tiene salida HDMI?
Still out there?
Estoy aquí.
Or do you have a connector?
Ah. El problema de redes general en Laguna, yo tocamos en la dirección general que está trabajando, pero creo que para pedirle una adaptadora. No tiene? Ah, okay.
You don't have a,
I didn't bring it with me,
Ah.
but let me check it.
Okay. I left my connector in my classroom in Texas. All right, so I'll talk a little bit about it since we have the time. Okay, so with the nuclear cross sections, and I have some pictures on here, and I'll draw some pictures up here for the rest of you. With the nuclear cross sections, you have a huge range in energy. And so the cross section, the sigma or sigma, and neutron energy in electron volts goes from 10 to the -5 all the way up to 10 to the 7th. And in general, you have kind of a range where it's kind of smooth, and then it gets to having a lot of spikes, these resonances. And then it'll get to a fast range where it'll be, gets kind of smooth again. And so that might be for one isotope, maybe uranium-238's total cross-section. And then, where those markers go? I picked one up from somewhere. I have another color here. All right, don't have another color. All right, I'll use this one. So then we might have another isotope. So that one might be uranium-238. We might have another isotope that might have some cross-section that comes down and then has its own set of resonances. And this one might be uranium-235. And so in that, we have 12 orders of magnitude. And so when we thought about the spatial mesh, we said a reactor is on the order of a meter, and our geometric features are on the order of centimeters or microns. This, we have an energy range that is covering 12 orders of magnitude, not just 5 in one dimension in space, but 12 in that energy. And so in general, what we try to do when we discretize this problem is we try to break it up into a set of more solvable chunks. And so if we said, you know, well, first of all, could I just call this one average cross-section? And if I just said, let me pick one average cross-section, then, you know, maybe for the U-238, I say my cross-section is right there. And my U-235, my cross-section is right here. And then I have one energy, and I have a 238 total cross-section and a 235 total cross-section, and I could solve the problem. But this was on a log scale. And so these changes in cross-section can go from maybe 10 to the -3 to 10 to the +3. And so in a very small energy range, you wind up with a very big change in those cross sections. And the two different isotopes, those cross sections might have big spikes in different locations. So what we want to do is we want to break this up into some chunks. So if we do one chunk, it's a, how do you define that average? I mean, this range from 1,000 to 10 to the -3, how do you pick, is this 19, 19.9, 25, 100? How do you pick what that average value would be? Or you could say, well, why pick an average? Why not just break this up into a whole bunch of energy groups this way? So I said, I'm going to do lots of these different energy domains. And so on each one, I pick an average. And I say, this is my average for that region. And now I have a set of energy groups that each have an average cross-section. Neutrons can start up here from fission at the high energy and bounce around and slow down and come to these low energies. And so they're scattering from this group to this group, and this one to this one, and this one to this one. And when I look at my resonances, if I zoom in on one of these resonances, like you guys have on the screen, there's a collection of these resonances. So if my continuous cross-section looked like this with some of these resonances, then I might break this up into chunks that look like this. And so I have tried to break that energy domain up to pick out all of those resonances. And so to do this, well, it might require 100,000 energy groups. If I really don't want to have much error here, maybe I break these up into even smaller ones. And so my number of groups could range from 1, but if I have one group,
how do I pick a good average value for that group? Or maybe I have 500,000 groups. But if I have 500,000 groups, then that means the problem I was trying to solve that had a huge number of spatial directions, or spatial cells, and a huge number of directions to travel, now also have a huge number of energy groups that are all coupled integrated set of equations. So the best way to do this is, wouldn't it be nice if we knew what a good weighted average was? So if we knew what the flux was, then we could figure out what a weighted average should be. I'm hoping you guys online can hear me, and speak up if you can't hear me. And so if we knew the really fine resolution and energy neutron flux, then that should be the neutron weighting function. And so if our flux in some range with a whole bunch of resonances, or if our resonances look like this in some range, then you will often have so if this is uranium-238 and you're in a huge infinite sea of uranium-238, where the cross section is really big, there's not going to be much flux because the neutrons are all going to get absorbed at that energy. Where the cross section is small, you're going to have a really big flux because there aren't neutrons getting absorbed at that energy. And so the neutron flux almost will follow the opposite of that. If I can draw this correctly, this being the opposite. And so this is my cross section and this is my flux. Then if I wanted to create some weighted average, then I could say a good average would be the integral over some energy range, delta E, of my flux, continuous energy flux, times my continuous energy cross section, over that integral dE of my continuous energy flux. And that would give me a weighted average. And so all I need to compute a good weighted average to get a one group is the solution to the continuous energy. But I don't know the solution to the continuous energy if I don't have I have to solve the continuous energy to have a solution to the continuous energy. There is a opposite effect. Let's see. The opposite holds true of, let's see, nope, I didn't get it into it. I'm going to get into it anyway, since I want the pictures for the rest of it. So,
This is, I don't know.
nope, that's not the right one.
Yeah.
Oh, wait, no, that's USB to, we need one that is HDMI.
Yeah.
So do you have a USB to HDMI?
No, but they are already looking,
Okay,
getting one from one of the televisions.
okay. All right, so if we had the opposite, so this would be the flux, if this was all U-238. So you're an infinite sea of U-238, then the flux would be small where the cross section is big. But if you're in a infinite sea of U-238, or you have a little tiny amount of U-238 in an infinite sea of water, well, there wouldn't be that big resonance, there wouldn't be that big absorption. The flux, if the water's cross section looked like this, then the flux might look like this. And so if the flux were smooth and didn't have the dips in the resonances, then the average is going to be a whole lot higher, because that average isn't going to be, the flux is mostly down here. The average is the flux is sitting here. And so you'd have a much higher flux if you have just a little bit of that U-238. And so the cross section you use for U-238 will depend on what the neutron flux is in that material as a weighting function. Does that make sense? All right. So, what we'd like to have some estimate for what the continuous energy flux would be in order to get a good weighting function
to create an average for a number of groups. And so if, for instance, we said, let's solve this with 1 million energy groups, and we could solve it with 1 million energy groups, then we could get a very effective cross-section that we use with 1 or 2 energy groups. But solving with 1 million is kind of the whole is the whole piece of the problem. So, let's see. So in general, with these reactors, the physical space that we have is really, really big. So we have our reactor core. We have a cylindrical reactor core. That's on the order of 10 to 15 meters. Or no, the full reactor vessel. Full reactor vessel is on the order of 10 to 15 meters. When we look at the reactor core itself, the reactor core has about an 8 meter diameter, and the reactor core's height is about 3 meters. When we look at the individual assemblies, so that core is made up of all of these individual assemblies. Each one of those assemblies has a bunch of fuel pins in it. Assemblies is on the order of 20 centimeters. Each one of those fuel pins inside of the assembly is on the order of 1 centimeter. And it has cladding, and it has an air gap, and then it has your fuel. But we talked about depletion and how the materials deplete, and that rim effect that I mentioned yesterday, where you have a whole lot more plutonium build up in the very outer edge of the fuel. And so in reality, if you want to understand the fuel and the isotopes in the fuel, you have to break, for a constant uniform material, you have to break that fuel pin up into multiple rings. And so if I zoom in here, your fuel might initially be UO2, but as you deplete the fuel and you change the isotopes, out here, you're going to get a lot more plutonium than you do in the center. And so you'll often put radial rings and say each one of these would have a uniform material, because when we discretized our problem, we said we want a cross-section that is uniform in each of these. And so with that, we wind up with, these regions being on the order of millimeters or less. And so we have 10 to the 4th cubed size of a problem in space. So our space is on the order of 10 to the 4th cubed, 10 to the 12th. Our directions that we look at, the directions that we have to consider in order to not make any approximations in energy, we're going to need on the range of 10 to the 4th to 10 to the 6th groups in energy. The number of directions that we consider, so directions, we're going to need in the range of 100 to 10,000. 10 to the 2 to 10 to the 4th. And so in total, it's working. No, let me turn mine off so we get on the room mic. Oh, wait. Oh, okay, that was just the TV. So we're not on that one. Are we on? Are we on? Are we full go back to normal internet again? All right, let me turn my audio off on here then.
All right. I'll come back to the whiteboard later on today. So I mentioned space. We need on the range of 1 billion to 1 trillion unknowns. Depletion makes it harder because depletion changes the materials from what they were originally. When we look at energy, the people online saw this picture before. This is from 1,000 to 5,000 electron volts. This is the total cross-section of uranium-238. And if you have a material that has some uranium-238 in it, then this would be that cross-section, the neutron flux. And so your weighting function would be some average of this with all of its complexity and that to create some weighted average. If you just use, let's pick that number and make it flat, it would be a very different average cross-section. So if we wanted no approximations, then we really would need in energy 10,000 to 1 million unknowns in energy. And in direction of travel, at any given spatial location, so if you pick out one location, the neutrons vary in direction a whole lot. And so there's a lot of complexity about what the magnitude of the neutron flux is at one location in different directions because there are different materials there. And so in order to resolve the directional variation, you need on the range of 100 to 10,000 directions model. And so to do that, could we do it today in one big shot? If we had a sodium fast reactor, it's fast energy. And so in general, we go, well, I don't care about anything below this energy. So I can ignore the rest of these energies and only focus on these fast ones. That makes it a lot easier. A sodium fast reactor is also a lot smaller in size. And so that smaller in size means we can get away with maybe only 10 to the 15th petabytes of unknowns just to store what is my solution. And 10 to the 15th petabytes. In a light water reactor, looking at all of these, adding them up, we're in the range of 10 to the 18th. So those are exabytes. And if you had a full gas reactor where I said that graphite is not as good as a moderator as water. And so in a gas-cooled reactor with a whole bunch of graphite, the volume is a whole lot bigger. And so because the volume is bigger, you need more unknowns. And so computers today have that much memory. The big, fastest, biggest supercomputers in the world. They are building computers right now that could have this type of memory. Probably in 10 years, 15 years, we'll have computers that have that kind of memory. And so, could we do it? Yeah, maybe for some types of reactors. But the answers we get right now aren't that bad. We have operating nuclear reactors. Do we really need a supercomputer just to do one state point for radiation transport? And there's also a whole lot of uncertainty. So in that nuclear data and all these cross sections, there's a lot of uncertainty that folds into it. In your material definition, you said I'm going to refine down to every millimeter. Well, a lot of the geometries have an uncertainty. I know my fuel height from this height, but the geometry is changing because things are thermally expanding. So there's a lot of other stuff. So there's a lot of uncertainty in our data. And in reality, when we talk about coupling with other physics, the other physics don't care about anything except what was my energy integrated and angle integrated values. For heat transfer, they say, what's my power? Well, the power is, give me the total energy produced from fission in this whole system at this location. It doesn't matter which direction the neutrons are traveling, the key caused that power. Similarly, with isotopic depletion, they wanted to know how many N gamma reactions happened from this isotope. It doesn't matter which energy the N gamma was, it just needs to know how many total N gammas happened. So there's a whole lot in that unknown vector that quite frankly doesn't matter. We really only care about this spatial thing, integrated overall energy and direction. So the stuff that we need to pass to other people is really only on the order of 10 to the 9th, 10 to the 12th, which is still big, but it's not nearly as big. Now, so in the traditional way of doing it now, We don't do it in that one big shot. That's no way we can do that because we haven't even talked about time dependence or coupled physics. So the way it works today is we do it in a 3-step process. We first have a bunch of different pin cell types, and we say, okay, how many fuel types do I have in the reactor? I have 3.5% enriched UO2. I may have a MOX, I may have a 4.5, I may have a burnable poison. I have a bunch of different pin cell types. And for each pin cell, I'm going to do very high fidelity and energy. Hundreds of thousands of unknowns. So I'm going to do this real continuous energy calculation. But I'm going to approximate what my temperature is, what my coolant density is. I'm going to approximate this as one dimension, or maybe even 0 dimensions in space. And so I might say it's just a 1-dimension radial radiation transport problem. In the fast reactor world, they say the mean free path is so much bigger than this one pin cell. It doesn't even matter. I don't even need to worry about 1-dimensional transport. I can just do infinite homogeneous medium. And so you do really high fidelity pin cell calculation to approximate the state and the boundary conditions. And then you use that flux that came out of it as a weighting function to get a new averaged cross-section. And with that average cross-section, now you can go to a bigger problem that has more geometry. So we say, let's take all of those radial regions and let's smear them together as one green fuel pin type, one purple fuel pin, one yellow fuel pin type. And I do a 2-dimensional transport calculation. And here's my full BWR geometry with my different water densities, with each fuel pin could have different average temperatures if we wanted. But we still have to approximate some boundary conditions. So we'd say, let's just assume that it's an infinite sea of these comparable ones. Let's just assume it's 2-dimensional, ignore everything that's axial. And let's evaluate what that neutron flux is with it. And now we have the neutron flux spatially everywhere. And then what we do is we say, let's do the same thing here we did with just energy, but let's do it with space too. Let's smear all of these complex materials together and homogenize them. And then we create one average smeared material, the red assembly and the yellow assembly and the aqua assembly, all surrounded by water assemblies. And here, now we have gotten rid of all of our complex geometries, our little fine millimeter scale things. Once here, we have big, large chunks, and we've reduced it from 100,000 unknowns to a couple hundred unknowns to now 2 to 4 unknowns in energy. And so once we've gotten down to 2 to 4 unknowns in energy, and we have all of these materials smeared, then we don't even have to do radiation transport any longer. We can do diffusion. If you guys aren't familiar with diffusion, you'll probably learn about it in a class coming up, but hopefully you guys are familiar with what diffusion is. It's an approximation to the direction dependence. And so in radiation transport, we say we're going to model all of these directions. In diffusion, we just say we're going to assume things are smoothly varying in direction and let them creep out. And so with this, we could get, here is my full 3-dimensional diffusion solution that has what is the neutron flux in every one of these cells, but it's only 2-group or 3-4-group flux. And if somebody said, well, wait a minute, this actually was composed of a real pin. Where is the highest power pin in this reactor? You'd have to go, okay, well, first let me figure out where the highest power assembly is. We'll call it this one. And then we have to figure out what the highest power axial height in that core diffusion was. So this assembly at, half a meter up is the highest power region of the assembly. And then we have to go back to this one and we say, okay, now which one of these pins was the highest power pin? Okay, this one was the highest power pin. So if we take the power from this pin that is bigger than the average, and we multiply it by the power that came from that one, that's going to give us the biggest power region in the entire problem. And so you have to reconstruct what your actual pin powers are from this coupling of the average smeared diffusion solution with the fine mesh 2-dimensional lattice calculation. And that's the way it's done now. If you really want to know what is the pin power distribution in a reactor, you have a code suite that does these things, feeds data to another code suite that does this. So, and then for those who aren't familiar, the one up top, this is called lattice physics. And this would be like a Casmo. And this is core diffusion. This would be a simulate. And so on your lattice physics, since you need to account for time dependence in multiphysics, you have to go through this process many, many times. Because you need to know how do these average material properties change as the fuel temperature changes, the coolant density, the boron concentration in the water. Was the control rod in or was it not in? And so you have a whole bunch of perturbations to what the state was, because in this two-dimensional and one-dimensional problem, you said, I'm going to define a state and use it. And so you tabulate my material properties as a function of the state. And then you also do depletion. And so in this, you go through and you deplete the material and you let all of those isotopes change as a function of time. And so in here, in addition to saying I did tabulate my cross-section as a function of all of these physical properties, I also tabulate as a function of how long has it been irradiated in the reactor. So I've created a big, giant diffusion problem. The nice thing about this diffusion problem is, if I have 200 assemblies and I want to have 25 axial regions in each assembly, then I'm looking at only having in the range of 5,000 unknowns. And so this problem has 5,000 unknown spatial cells and 2 energy groups and just one direction, because it's the average, the integrated direction. So this problem only has 10,000 unknowns. That you could hand to MATLAB. You say, hey, MATLAB, solve this problem, and it takes care of it easily. So I've created a problem that can be run on one processor, very easy and simply, but I had to do a whole lot of work in advance to get to that point. Does that make sense? All right, online, you guys got any questions?
Doctor, sorry. So in core is when diffusion happens?
It is when diffusion happens.
Yeah, only in the core?
Yeah, so in general, when you run a lattice physics calculation, so you're doing transport on this pin cell, and then you're creating these average properties and doing transport on this two-dimensional cell. And then you're averaging these materials and groups, and you're doing a diffusion approximation. And so this one, since it's only one-dimensional transport, you might only have 10 to 100 directions. This one, since it's 2 dimensions, you still may have hundreds of directions. But when you drop down to this one, you smeared all of that material complexity away. And so you only have that one, the scalar flux that you're solving for. And so with diffusion, you're just solving for that scalar flux. Does that make sense?
Yeah, so cool. Thank you.
What was that?
Yeah, thank you, doctor.
Okay, good. Okay, so that was the in-depth how things are done with neutronics. But that's only one physics. And we know we have fuel performance and fluid dynamics and depletion, and we might have chemistry to deal with also. So what does this look like in the world of fuel performance? Well, so in fuel performance, we know that there are lots of complex geometric changes that are happening. We talked about all of those yesterday. The shape and the geometry is changing a lot throughout the life of that fuel tank. We know that every single fuel pellet is connected to the others, not in its material properties, but it can conduct heat axially, it can conduct heat radially, and when it releases fission gases, the fission gases mix in the plenum and in the gap around every one of those fuel pellets. The creep down of the cladding onto the fuel pellet is impacted by where it is. And so if it is down here near the bottom where there's a big solid plug of metal, it won't creep down as much because that plug is going to stay that size. So it isn't going to change shape as fast. But up here in the middle, 1 meter high, now it's nowhere near the plug that's constraining it. So it can change geometries more. And so there are things within that pin that make each different axial height connected. But every fuel pin is completely independent. There are 50,000 fuel pins, and pin 1 doesn't care at all about pin 2. So unlike the neutronics, where the neutrons will go from fuel to fuel to fuel to fuel, once you've identified a fuel rod, it's completely independent. So you could do 50,000 completely independent calculations if you wanted to know what was happening in every single fuel rod. So rather than try to solve that in full 3-dimensional space, where we're trying to mesh the entire fuel rod, the approximation that is made in the traditional codes is 1D heat transfer. So we say, you know what? The only thing the other physics care about is how much heat comes out the outside, the surface, and what was the average temperature of the materials inside. It's the only thing the other physics cares about. So that means temperature is what we care about most. And yeah, there's going to be some axial conduction, but most of the heat is coming radially out. You have cold water here, and you have really high power on the center. And so almost all of it is just going to be one-dimensional radial conduction. But those geometric changes are really changing what that gap width is. That gap width could go from relatively big, which would cause a 300-400 degree jump in temperature in the fuel, to completely zero, where the fuel and the cladding are touching. And so you need to have some way of getting some thermal resistance in the gap. So all of these 3D effects affect how wide the gap is and what is in the gap. If it's pure helium, like it was filled with originally, helium has good conductivity. Xenon and krypton, the fission gases, don't. And so you need to know how wide is the gap and how much fission gas is in it. And so what you do is you say, let me just create a model. Let me create some effective gap thermal resistance model. Let me make it a function of temperature, power, burn up, pressure differences, whatever other things that I want in there. And then I go and I create a bunch of experiments. And I say, let me compute what the average temperature is inside when I change the power level. Let me create 3-dimensional models of this. And so there are thermomechanics fuel performance codes that are in RZ, 2-dimensional, radial and axial, or full 3-dimensional. And let me do full high fidelity calculations to determine how does that effective thermal resistance change as a function of all of these other things. And I create a model similar to in the core diffusion. I created a interpolated function where I could say, let me get my cross section as a function of all of these other things. Here I'm saying, let me get my gap thermal resistance as a function of all these other things. And then I wind up with, if I had it calibrated well, then I wind up with a simple 1-dimensional thermal conduction model that I could use at every one of my 25 axial heights. And each one is maybe 10 mesh cells, maybe 4 or 5 mesh cells, because it's nearly an analytic solution. You could derive that analytic solution to what that temperature is. And so I might have only 5 unknowns for each one of these, each axial height for each one of the 50,000 fuel rods. So now I've reduced this to, okay, well, if it's 50,000 times 25 times 5, that's still pretty big. And when I did my neutronics, I didn't really tabulate everything as a function of every fuel rod's temperature. Generally, we would say, let me just say all of the fuel rods are the same temperature. Now, all the fuel rods are a new temperature. So I really don't need 17 by 17 temperatures. I really only need one temperature that's the average temperature for fuel for the assembly. And so instead of doing every 50,000, I'm going to say, why don't I just do one rod as representative for the entire assembly? And so now if I had 25 axial regions and 200 assemblies and 5 unknowns per rod, now I'm back down to a manageable size. Again, I can solve that problem. I can give that to MATLAB and say, let's solve it, let's get that answer. Thermal fluids is also a problem. So in light water reactors, there is always boiling. In a boiling water reactor, it's heavy boiling. But in a pressurized water reactor, there is subcooled nuclear boiling that is happening. In any accident in a light water reactor, you always are concerned about boiling flow. So every single light water reactor has to deal with boiling flow, and boiling flow is incredibly complex. Depending on what the velocity is and what the void fraction is, the ratio of void to total volume, you can have your flow in very different geometries. It can just be your gas is flowing along at one speed, your water flowing along at another, or if that gas velocity increases, it's going to start to create waves, and it's going to create this stratified flow. As you increase more and more of these, the water content, then you start to get big chunks, plug flow. But if the bubbles are really tiny because of the problem and the chemistry of the water, then you might wind up with this bubbly flow. Or you get really big chunks of air that are coming in slugs. Or if there's boiling happening at the bottom, then you can wind up with a little bit of water at the bottom, a little film of water at the top, and it's mostly vapor through the middle with little droplets of water on the inside. It actually can do the opposite too. It can have mostly water in the inside if it's boiling, if there's heat transfer, then you can have liquid water in the center and you can have vapor on the outsides. Intermittent flow, so it's just varying between each of these as a function of time. Or mist flow, where it's almost all vapor, but with little droplets of water inside it. And so in two-phase flow, it is very complex on what that structure is. So adding to that, we also have very complex and very tiny geometric structures. So all of these little fins that are coming up that are designed to induce turbulence are very thin metal structures. These springs that touch the fuel rod wind up touching at circle-to-circle points. And draw that over here so people online can see it. And so whenever you have a geometric structure, that's not a marker. There's a pencil in the way. So if you have a fuel pin here, and you have your grid structure here, and it has a little dimple sticking out to help hold it in place. And up on this side, it had a little structure that looks like that. Those are two different types of springs that can connect. When you're modeling this flow, if you really want to understand the flow and the complexity of the water, let alone the water plus the vapor, you have to understand how is it flowing around all of these little complex structures, because those complex structures will change the velocity and the average density and what type of flow it is. So the fluid dynamics is incredibly complex. In general, we have a huge field of computational fluid dynamics, and there are levels of fidelity solvers in computational fluid dynamics. In your direct numerical simulation, you effectively say we have no approximation. We're going to model this completely. We're going to get all the physics right. But our mesh has got to be smaller than every geometric feature and every eddy current. So in that, even if we have flow going here in a pipe, there are going to be these eddy currents where the flow will kind of recirculate as there's turbulence. And some of those eddy currents are really, really tiny eddy currents. So in DNS, you have to mesh this problem so that mesh is smaller than every one of the large eddies and the small eddies, and every one of these geometric features you get resolved completely. And if you have two-phase flow, it also has to be smaller than your bubble size. because you're separately modeling, here is this bubble flowing and this bubble. So your mesh has to be smaller than your bubbles, and your bubbles can vary in size from slug to little tiny pieces. A more approximate way of doing it would be a large eddy simulation. On large eddy simulation, you say, let me just ignore these small eddies. Those are too small to matter. Let me put in some terms that will account for these small eddies. And if I have small bubbles, well, let me put in some terms to account for those small bubbles. And now I've created sort of an approximate DNS simulation. But I still have to make sure that my mesh is smaller than these eddy currents and smaller than all of these geometric features. If I go one level coarser to Reynolds average Navier-Stokes, that's going to say, you know, forget about all these eddy currents. These eddy currents, if we did DNS and LES and we did a bunch of experiments, then we can determine the effect of those eddy currents. Those eddy currents will affect heat transfer, how quickly the heat goes from the surface into the fluid. It will affect the overall velocity of it, but you know, we can just create some models to account for that. And similarly, with Reynolds average Navier-Stokes, we're not going to model bubbles individually. That's way too complex. We're just going to have a effective, here is a fluid velocity, and here is a gas velocity, and they have their own velocities, and we're going to treat it. But we still have to make sure that we mesh this smaller than these grid spacers. And so you wind up saying, okay, let me put my mesh in here, and my mesh is starting to look like this to get that flow. And where these circles come together, when you have circles touching, you have to have really, really tiny mesh cells in there. And you wind up filling this problem with these mesh cells that are around these little knobs. And you say, you know, that's too hard. But if I would just approximate this geometry as this, then my mesh cells could be a whole lot bigger. And now I could get some bigger mesh cells in here, and I can have a much easier problem to solve because I have larger mesh cells. And so I start approximating what my geometry looks like to make the problem easier to solve. Because those grid spacer, those geometric features need to be resolved, or they need to be accounted for. So if that's still too big, then you could go to something called subchannel flow. Now, subchannel flow is going to say, you know what? Forget about all that stuff. Let's just model this. Okay, you guys can't see this. The subchannel flow is going to say, I know I got a bunch of fuel pins that are in a square array. And I'm going to pretend that everything here, this is all one mesh cell, right here, going down some height. And so that region, if I draw it up here by itself, get my artistic skills to the test here. That is my mesh cell. And now I have one mesh cell per channel. So this is maybe 1 centimeter across, maybe 1 centimeter tall. And now I say, all right, I'm going to get heat transfer from here, the pins into the fluid, and I'm going to have my flow, and my flow is almost entirely vertical. There may be a little bit of flow that goes sideways, so I need to have some accounting for flow that goes sideways, but I know most of that flow in this geometric structure. I'm pumping in from the bottom. It's supposed to go out the top. The flow is mostly going all vertical. And I can treat this and I can say, wait a minute, I have enough data because I ran a bunch of experiments that I can say, given some velocity and other parameters of the fluid, then I can say, I know that there is some ratio of fluid gas velocity to fluid velocity. And I might have some times where I have a different film of fluid around the rods and the rest is vapor, or maybe I have a film of vapor around the rods and the rest is fluid. And so I create this structure where I say, you know, let me treat the flow as mesh cells like this, and let me have some models that I can calibrate with CFD or with experiments to tell me what fraction of the flow goes sideways, and what is the heat transfer coefficient as a function of all of these different things, and what is my fluid and vapor velocities and things like that. And so now I can create this sub-channel model that is on the range of every channel. Every channel is modeled individually. And so that would create a mesh that's on the order of 1 centimeter squared. But if I wanted to, I could use the exact same type of thing and say, let me just model that entire assembly. Pretend that's 17 by 17. And I'm going to say all of this, which is 20 centimeters by 20 centimeters, and maybe I have this 20 centimeters or so also. All of that I treat as one subchannel. So all of the flow in between all of these regions, I'm treating as one. And there is some perpendicular to the direction of flow that goes back and forth. But most of the flow we know is going vertical. And so I've created this very calibratable thing. I have to have a model for how much does the pressure drop when I go across a grid spacer? How much does it drop when I go across the pump, when I go across the heat exchanger? What is my heat transfer coefficient as a function of the amount in the liquid phase or gas phase? And so I create all of these highly calibrated models that I tune with experiments, that I tune with simulation, and it gives me something that has mesh cells that could be on the order of 200 centimeters squared because it's modeling the full assembly. So in doing so, if I'm modeling the full assembly, then I'm looking at 10 to the third type of unknowns. If I'm modeling every individual channel, I'm looking at 10 million mesh cells. Reynolds average Navier-Stokes, at least 10 to the 12th. Jumping up the large eddy simulation, at least 10 to the 19th. Direct numerical simulation, 10 to the 24th mesh cells. So there have been people that have run Reynolds average Navier-Stokes on our supercomputers for an entire nuclear reactor core and gotten the flow with all of these approximated grid spacer geometries to get that flow distribution throughout the core. In doing so, they can generate data that helps us understand how well that subchannel is working or calibrate that subchannel. But in general, we aren't doing this for full reactors, but we certainly could use large eddy simulation in flow through a grid spacer to decide what would the pressure drop be through a grid spacer. What is that heat transfer coefficient that should be through a grid spacer? So maybe not using that for the full reactor, but using it for regions of the reactor, it can be very beneficial. And so with our calibrated thermal fluids, we will use a sub-channel capability with an assembly-sized mesh. We'll have a whole bunch of experiments that determine these pressure drops, the amount of mixing between coolant channels, the gas to fluid velocities at different regions at different times, the heat transfer coefficient as a function of all of these things. And that's going to give us, you know, here is my model for all of these things as a function of mass flow rate and temperatures and pressures and these other things. So I've created a now relatively solvable problem for each one of the physics. In my core diffusion, I have two groups. I have no directions. I have 200 assemblies and 25 spatial mesh. So I have 5,000 spatial cells. My subchannel thermal fluid, I need to solve for velocity in one direction, Z, my temperature and my pressure with about 5,000 spatial cells. My fuel performance, I have one representative rod in each of the 5,000 spatial cells, and it does a 1B analytic conduction with 5 spatial mesh regions. And so I wind up with, that should have been 5,000. I need to switch that. 5,000 to getting up to 50,000 total unknowns. 50,000 unknowns, we can solve that on a single processor. It may not be, you give it to MATLAB and you say, hey, MATLAB, invert this matrix. You might have to write a better iterative method solver to do it, but this is something that we can do on one processor. Your laptop can do that problem. Your phone probably can do that problem. So, what questions do y'all have before I move on to this? Online, you guys got any questions?
Yeah, it's me again. I have another question, Doctor.
Doctor, I have a question too.
Please, whichever one go first, either way.
Sorry, did you say in Navier-Stokes gamma flux?
We didn't hear what you said.
Sorry, did you say gamma flux in Navier-Stokes?
If you are considering gamma
Oh,
fluxes.
gamma heating?
Yeah.
So I'll talk about that. Yeah, let me talk about that for a minute. So, he is absolutely right. Most of the power in a reactor is coming from fission. The fission is depositing most of its energy locally in that material where it fissioned. But some of that energy is carried away in the form of neutrons and gamma energy. Some of those gammas are prompt gammas as soon as the fission happened, and some are from decay of radioactive fission products. And so the neutrons are traveling, carrying some of that energy away, and it isn't going to be deposited locally in its immediate cell. It might go and cause another fission, and it does the same thing, but it might go and get absorbed in a different material. And if it gets absorbed in a material, it will deposit about 3 to 4 MeV. The fission is going to release about 200. When a neutron gets absorbed, it's going to release about 3 to 4 MeV. And but some of that energy, a few percent, is in gamma energy. And the gammas can travel even further than the neutrons. So in the core diffusion solvers, they usually have a gamma correction. So they don't actually do radiation transport modeling of the gamma. They did some gamma radiation transport modeling once, and they said, you know, most of that energy gets deposited in this assembly, and then, you know, I think 80% in this assembly, and 15% in the nearest neighbor assemblies, and 5% in the next nearest neighbor assemblies. And so they just kind of smear that gamma power around. They aren't modeling it directly. Does that make sense?
Yeah,
I have a question.
Yeah, what's your question?
Okay, Dr. Kevin, how do you consider the Current limit of the Current number for the selection of the mesh?
So for those who aren't familiar, the Current limit says that when you are defining your time step cannot be big enough that the fluid is going to flow beyond multiple cells. And so if we had this problem with these tiny cells, and each cell were 1 millimeter, and you had a velocity that was 1 millimeter per second, then your time step, so we haven't done time discretization yet, but if we did a time-dependent problem, then we would have to break this up into discrete time steps. And you could have big time steps, or you could have small time steps. The smaller the time steps, the more accurate it is. The bigger the time steps, the more error you're introducing. But with fluid flow, if you have cells, let's say we have this one-dimensional cell, and each of these is 1 millimeter, then you don't want your time step so big that the fluid from this cell goes all the way over to this cell in one time step and never touch leaves. And so your Current limit is saying you want no more than 50% of the fluid from this cell to go into this cell to try to slow it down. And so the smaller your mesh size, the smaller your time step size is. If you have mesh cells that are on the order of 20 centimeters, you can have big time steps. Your mesh cells get down, or if your mesh cells get down to 1 centimeter, you have to have smaller time steps. If you do Reynolds average Navier-Stokes, it gets even smaller. So yes, that Courant limit is a big challenge, and that's why most of the time they are solving a steady state or time marching it to steady state for the fluid flow problems.
Thank you, Doctor.
Any other questions?
Yeah, what about the CFD? Is the CFD used also for a transient?
So how do you use CFD for a transient?
Yeah, that's right.
So you can. So that's going to go towards the higher fidelity. So today I'm talking about the low fidelity. Tomorrow I'm talking about the moderate fidelity, and then there's the extreme fidelity. The preview, this is moderate fidelity, and this is extreme fidelity. DNS and LES, we're not there yet for coupled physics. But yes, so if you know a power distribution that varies with time, you can hand that power distribution to a CFD code and say, given this power distribution, solve for what my temperature and flow distributions are. That can be done, but you have to know that power distribution a priori. And if you're trying to solve a coupled physics problem, you don't know it necessarily. That makes sense?
Sure.
All right. What other questions you guys got? All right, so for coupled physics calculations, if we do steady state problem with time dependence, so reactor depletion, the reactor goes on full power, stays at full power, operates for a year and a half, and shuts down. For each time step, you solve a coupled neutronics, fuels, and fluid problem. This neutronics is a k eigenvalue neutronics problem. Then you have, here is my flux distribution, here's my power distribution. So now I can deplete my fuel to new isotopes, and I have a new isotope distribution. So then I go to my next time step and I solve my coupled neutronics, fuels, fluid problem again. Over and over, you're solving this k eigenvalue coupled neutronics, fluids, fuels problem. If I do an accident type of problem, I have a loop over each time step. And when we discretize in time, we effectively add a source from the previous time. So to show you in transport terminology with operator notation, we have our 1 over s d psi dt plus L psi equals Q. We need to make some approximation for d psi dt. And so we're going to say psi at time 1 minus psi at time 0 over delta t. And I'm just going to make it 1 over s. And I'm just going to make a finite difference approximation to it. And then I say, all right, that's equals L psi. I'm going to put a star here for now, equals Q. So in my time discretization, if I made this psi, if I made that psi 0, then it is a very simple thing. Psi 1 equals psi 0 plus or minus S delta T L psi 0 plus S delta T Q. I never actually do a coupled physics solve. There is no invert L. But it's actually a really terrible approximation. So don't do that. So that's a pure explicit approximation. An implicit approximation, a pure implicit would say, let's make this psi 1. And now what we've done is we've created something that is a L plus
1 over S delta T. Psi 1 equals Q plus 1 over S delta T psi 0. And that is the same as a L star psi 1 equals Q star. I just add in the time dependent pieces. And so with time dependence, we effectively will do a similar, we still need to invert that problem. And if this were coupled physics, it would follow the same thing. We would add in some source from the previous time, a little bit on each side, and then we solve our coupled neutronics fueled fluids problem. How we do that, I'll do that more on the whiteboard here. For all of these, we wind up following this. In neutronics, you also have delayed neutron precursors. So for those who aren't familiar, instead of solving a k eigenvalue form of psi, you would solve another set of equations where you account for delayed neutrons. But the general structure of how you do these things follows the same type of mold. So let's see where I'm at time. 15 minutes. All right. So any questions on that before I jump into iterative methods for this? So I said that we had 50,000 spatial cells, and we have, so in space, we have 50,000. In neutronics, we have two groups. In fuel temperature, we have 5 spatial regions. And in flow and thermal hydraulics, we have temperature, velocity, and density. And so we are looking at 3. So I'm going to throw in some operator-ish notation and say I have some neutronics operator N that takes in a fluid solution and a thermal hydraulic solution and produces some neutronic solution. And so if I had some initial guess at guess I for the fluid and the thermal hydraulics, I'm going to produce some neutronic solution at I. If I have a fuel solution, it's going to take in a power from neutronics. It's going to take in the temperature on the coolant from the thermal hydraulics, and that could produce some new fuel estimate. And my thermal hydraulics could take in a neutronics power and a fuel and produce a new thermal hydraulics. And so I could have each one of these physics as completely independent things. They could actually be completely independent codes. So I could write a code to solve the neutronics and dump an output file. And I could write a code to do the fuel and dump an output file. And my thermal hydraulics code could say, let me read his output file, and generate my new output file. And then I could just have a script. And I could just have a script that says, a Python script that says, call this one, 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 call this one. And I could just march between them, all writing to their own files. That absolutely can be done. In fact, there are a lot of people that have done a lot of really good research doing that exact process. It is often cleaner if you can put it all inside of one code. And now you say, let me have one code that does all of those things. And so now my one code knows about one mesh, and I don't have to worry about, wait a minute, did I read the right location in the fuel size to the right mesh cell? Because it's one code that knows all of this stuff. So I can have one code that wraps all of those things and it does the same thing. Solve, 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 solve.
and I just march until I'm happy and I'm done. And well, actually, I should put these in I plus ones. Otherwise, we're never actually incrementing the solution. So we loop I equals 0 to converged. And so I'm just marching through, and each time I get a new neutronics, a new fuel, a new thermal. Now with those new ones, I jump to the next one, and I'm just marching through. And with that process, this can converge to a solution. It is always going to converge pretty slowly, and it will often not converge. And so, for instance, our general, if we have one-dimensional diffusion, let's say we have a reactor that is really large, acts radially, or is really big radially, and we have flow up here, and so we have some power distribution. We say, oh, the neutronic says the power is some cosine shape. Highest in the center, lowest on the outsides. And now my fluid flow comes in, and my fluid flow, or my fuel temperature solve, takes the power and says, okay, let me compute my temperatures. And so based on the power being highest in the center, it's going to say, oh, well, my fuel temperature is also like that. My fuel temperature is really high in the center. Well, the next time I come through, my neutronics will say, oh, wait, if that fuel temperature is really high, then my cross-section there needs to be highly absorbing and not nearly as efficient. So now I'm going to drop the power. So now my power is going to look like this. Because I had a high temperature in the center. And so then when the temperature solve says, hey, I have a low power here in the center, now let me give you a low temperature. And you just iterate back and forth between them. And it gets into this oscillation mode where it goes from cosine to basically a double cosine. And you just go back and forth, and it never actually converges. In fact, it can diverge. This next one might be a bigger cosine, and then an even bigger dip, and then an even bigger cosine. And it just explodes and doesn't converge as you go marching through that process. So you can do that. And there are times and there are states where it works. And there are people that have done full research projects on how do you stabilize this. And so one of the ways that you could stabilize it, you could say, wait a minute, every time, let me always use the latest. And so if I did neutronics first, then let me use neutronics at I+1. And here, I can do I+1 and I+1. And then when I get to the end, before I get done, let me call these stars. Let me say my new n at I+1 is 1/2 of my old n at I plus the new n that I calculated, I+1 star. And let me do the same for my fuel and my thermal hydraulics. And in fact, why make it a 1/2? Why not make it a alpha and a 1 minus alpha? And so each of these, I am dampening how much of the new solution I give to the next iteration. So now if alpha is 1/2, then half of it's the new and half of it's the old, and now I can get it to converge. And so with this process, when I put in these dampening factors, I can get this solution so that it will converge most every time, but I might need to play with those alphas in order to get them to converge. And it might converge really, really slowly, but it can get there. So with this, I can also adjust which order do I change these in. So since I'm using the latest and greatest, maybe it would be better if I did, let me do thermal hydraulics and then neutronics and then fuel and change the order. I could have different alphas for each one of these things. And so there's a whole variety of ways that I could play with this scheme and make it work. The beauty and the benefit of this is every one of these things can be developed independently. You have a neutronics expert that writes a neutronics code that understands what the neutronics needs as input and understands its data and how to do it, And that neutronics code can do what the neutronics code does, and no one needs to know anything about it but the neutronics owner. The fuel and the thermohydraulics. This fits with the way that engineering used to be done. The reactors that have been mostly designed, you would see that at Westinghouse, at General Electric, in the US Navy, there were buildings of neutronics buildings and buildings of thermohydraulics buildings. And they would literally write code to do neutronics, giving temperatures, and then pass a file and say, hey, here's my output file. These are my power, this is my power distribution. And the thermohydraulics people would take that file and put it into their own input and then run their own calculations and say, here now are your temperatures, your densities, your velocities. And so this is how engineering was done. There was no coupled physics. It was one at a time, engineer to engineer, pass it over the fence. And we've designed and built reactors that way. So I'm not going to put it down as it's useless, but it is really, really inefficient computation. As we start to put the physics together into a single code, you have to get your different physics people talking to each other in person. But that's good, because then they start to learn and understand from each other in person about what the realities are. For instance, do we have one fuel temperature for the entire assembly? The fuel person would go, wait, you're doing what? No, it's probably not a real good idea. And you can start to explore together. Should we have different temperatures? One for burnable poison, which we know is a lower power, and one for the fuel itself. And you can start to explore and discuss and decide, how do we want to model this? How do we treat these approximations? How do we make sure all of these things are consistent and understood? And so by creating a single unified code, you can begin that communication and working together as engineers. So when you're looking at a Casmo simulate type of, or a simulate type of thing, you also have an iterative method for your neutronics if you're doing an eigenvalue problem. So in your eigenvalue problem, you have a variety of groups and a variety of spatial cells, and it's just diffusion, so you don't have a variety of directions. But in it, you wind up with the leakage psi for a given group in all directions equal minus the scattering from all groups G prime to G to all of, this is diffusion, sorry, we're going to use phi. All groups to my current group phi G, that's G prime, is equal to 1 over K, my fission operator, which goes from all groups G prime into my current group. This seem familiar to you guys, or did I take a step too far? This familiar from the operator notation? Let me draw it. So in transport, this would be omega dot grad psi for some energy group G and direction M, plus sigma T for energy group G, psi G and M, minus the integral of scattering 0 to 4 pi. We discretized in energy. This is a sum from M prime equals 1 to M, capital M, of sigma scatter from G prime to G. Exit, we back sum over groups here first. Sum over all groups, G equals 1 to G. Sigma scatter from G prime to G. And the sum over all my directions, M equals 1 to M. To make it the integral, I have to give it the weight in psi M for this given group. And so this is for a given group in a given direction, I have scattering from all directions and all energy groups into my current group G. And I divide it by 4 pi, because that's covering all directions. So that puts it into my direction. Is going to be equal to 1 over k, 1 over 4 pi, all directions, chi, because that's the distribution in energy. So the fraction of fission neutrons that come in my group. The sum of G equals 1 to G, nu sigma F of G prime, oh, that's G prime, M prime and G prime. And sum from M prime equals 1 to M, Wm psi of M, G prime. M primes. So that's the eigenvalue form of the transport equation. If I make the eigenvalue form of the diffusion equation, then this becomes a negative grad D grad phi for given group. There is no direction, plus sigma T for that group, phi G, minus sum of G prime equals 1 to G, sigma scatter from G prime to G of phi G prime equals 1 over k, sum of G prime equals 1 to G, chi G, nu sigma F G prime, phi G prime, which this is L phi. This is S for group G. This is G prime to G for all G primes. And this is my 1 over K F G prime to G for all phi G primes. So an L phi minus S phi equals 1 over K F phi. And I have that for all groups G equals 1 to G. That make more sense? All right, in the room, I'm getting some nods. You guys got any questions online? Okay, so this is just the diffusion operator. It's just space. If we set up an iterative scheme where we are going to iterate through a solution, then we could say, let me loop in iterations I. Let me first guess B and K. And I'm going to say, with that phi, let me compute a source. So let me loop over groups. Loop over G equals 1 to G. And let me compute my source for that group G is my 1 over K at iteration I plus my fission source, sum chi G, nu sigma F G prime, phi G prime. And then I do my inverse, so my phi at G, iteration I plus 1, is my Q G of L inverse, LG inverted, Q G. And now, so I computed the source for that group, computed the flux for that group, and I marched through every group to get all of my group fluxes. And then I compute my new K. K at I plus 1 is K at I times this, I'm going to call F at I. No, this doesn't have any G in it. The G is out here. So this is the same for every one of the groups. So that is F at I plus 1 over F at I. If I get a new K, and then I end. And in this process, this is just straight neutronics. There's no coupled physics at all. And so I'm guessing some flux. I'm marching through every group to compute what the group would be given that fission source. With that fission source, sorry, I needed the scatter source in here too. Q. Compute my source, solve the diffusion problem for that group, and I loop over groups. I get a new K. I iterate until is K converged, K and phi converged. If it's converged, then I exit. Otherwise, I go back and I keep going. This is do while phi and K are not converged. And so in just my pure neutron diffusion problem, I'm doing that over and over. In that process, I'm getting closer and closer to the correct neutronic solution. And so one of the other ways that people have explored how to do this more effectively is to start putting in my feedback from the other things in here. And so in here, I can say, okay, I did my neutronics. Now let me do my fuel and let me do my thermal hydraulics. And then I check my convergence. And so now, once I've put these independent physics codes into one code, and I say, I'm going to solve all of these at once, now I can start to look at, well, should I restructure how I solve this? If neutronics is solving in this way, maybe I need to embed these inside of this iteration scheme because it's all one code, and I can start to look and explore different options and different ways of doing this. And the same holds true for time dependence. And so on this, you'd still have a loop over time. And out here. That's all I have time for today. But hopefully that gives you an idea of, if you're using Casmo and Simulate, this is what's happening under the hood in all of these different physics domains. So Casmo or Simulate has inside of it, it is mainly known as a big neutron diffusion solver. But it has inside of it a fuel model and a thermal hydraulics model also. And so it can do this full coupled physics inside of it if that's what you ask of it. And that's how it is doing these things and creating these models. So any questions? Look at that whiteboard. I'm not sure that's what it means. Online, can you guys see the whiteboard clearly enough?
Yeah, it looks nice.
Okay. Despite my handwriting. All right, what other questions do y'all have? Oh, we're only 5 minutes over. So if nothing else, then that's all I have for today. Tomorrow, we'll increase the fidelity of all of these things and talk about how things change when we try to do things at a higher level of fidelity. Did you have something?
Yeah, she wants to know about how good is the thermohydraulics model inside the Casmo simulator. If there is something, if there is feedback or something inside the code in order to.
So I haven't looked at it, but my understanding is it is this same thing. It's assembly sized flow. And so you can give it a, here is my core flow inlet, and it has built-in parameters for pressure drop across things like that. And Simulate can be linked with
Simulate 3K.
a Simulate 3K, yes. Yeah. So I usually call those the same thing. Simulate 3K is, it has the core model, plus it has the full loop. So you have, your control rods can go in, your pressure, your pumps can change flows and things like that. And so Simulate 3K has the Simulate diffusion plus the temperature feedbacks and all of those things.
You need to activate it beforehand can simulate some cars in order to make the link with simulate.
With Simulate 3K.
If you don't, you cannot.
You don't get any feedback. Yeah, so I have, I've never actually used Simulate. I've used Casmo a bunch. I've done a lot of the lattice physics calculations. And then I've done a lot on the jumping higher in geology, but I just know conceptually how it's done at the core fusion. But people like Gustavo are probably much better experts on Simulate 3K and what it's doing, or how to use it at least. All right, thank you, and we'll see you tomorrow.
Anybody in the internet has another question? That's okay.
No question. Thank you.
All right. See you tomorrow then.
See you.